and we should continue on from where we got to yesterday. So remember that yesterday we
I will start just by reminding you about where we are in this.
We discussed the torsion and the curvature, and also parallel transport and geodesics, which kind of preceded that. So we essentially discussed different ways of making derivatives in the general manifold. So today, what we're going to do is to move with a concept that is a priori not related to differentiation. However, you can relate it to differentiation and then relate it to the geometry of the manifold, as we will see towards the end of today. And the concept we are going to discuss is called the metric tensor. Now, in everything that we have discussed so far, when we have been talking about manifolds, we have never seen anything like an inner product. So we have so far not seen an inner product. So in general, an inner product, if you look at the Euclidean space, it's a map from two vectors, and it takes an inner product of two vectors and it returns a number. And that number, if you take the inner product of a vector with itself, it's the length squared of the vector. If you take it between two vectors, it's the product of the length multiplied by the cosine of the angle between the vectors. So let's start today by looking at the generalization to manifolds. So the only linear product we have had, or the only way we have had to map vectors to real numbers so far, has been these dual vectors. So let's just discuss what we want an inner product to satisfy. We want from an inner product. So first of all, it should be a map taking two vectors to a real number. So it's a map taking one vector in the tangent space of the manifold at some point, and another vector in the same tangent space, and maps that to a real number. Furthermore, we want that it should be, first of all, it should be linear. So this means that if I take A1 V1 plus A2 V2, and I take the inner product with W, the linearity tells us that this should be A V1 inner product with W plus A2 V2 inner product with W. So this is the linearity in the first argument. We also will require that it's linear in the second argument, but that's going to be also a consequence of the second property that we want the inner product to have, which is that it should be symmetric. So that is that if we take V inner product with W, that should be the same thing as W inner product with V. And finally, the last requirement is that it's positive definite. So that means that if we take a vector V and we take the inner product with itself, this should be, well, we define this as the absolute value of V squared, or V squared. This should be greater than or equal to 0. And if V squared is equal to 0, this should imply that the vector V is the 0 vector. So we really want it to be positive definite and not positive semi-definite. So let's now discuss what these requirements tell us. Well, the first requirement, the linearity, already tells us that the inner product has to be a 0-2 tensor. So it's a linear map taking two vectors to a real number. That means that it is a tensor. So this is going to tell us that the inner product is related to a 0-2 tensor. And then we're going to call this tensor G, and it's the metric tensor. Now, in general, of course, on a manifold that is not already equipped with a metric, or that doesn't have a natural metric in some sense, there may be several choices in how you assign this metric. But this is the properties that we're going to require of the metric. And then the other two requirements just put further constraints on the metric. For example, if you look at 2, which is the symmetry property, that just means that if you take G acting on V and W, that must be symmetric, so that should be equal to G W V. Now we can also already start discussing the geometry here in terms of angles and lengths. And so if we have a metric that is some 0-2 tensor that satisfies all of these conditions, then the length of a vector is defined as having the length squared of the vector, that's given by the metric with the vector put in both arguments. And similarly, the angle between two vectors then we're going to have something like the following. So we're going to have cosine theta. That is going to be G acting on V and W divided by the length of V and divided by the length of W. So this is kind of the definition in a metric space of what it means to have an angle between two vectors. And you will recognize this, that if we go to Euclidean space, this would just be V inner product with W divided by the absolute values of both vectors. And you know that this inner product and in Euclidean space, that's just the absolute value of V, absolute value of W, times cosine theta. So what you would get left in that case is cosine theta indeed. So we're going kind of in the opposite direction. When we looked in Euclidean space, we defined the metric based on the inner product, but in a more general setting, we actually do it the other way around. We look at the metric and we use the metric to define what lengths and angles mean. So just to take an example, we can use this to consider the length between two very nearby points. So let's take now, let's take some manifold, and let's take 2 points here. Let's take P and Q, and they are separated by some small coordinate differences, dKa. So dKa here would be very small numbers, which means that this vector here, this transition vector from P to Q, would be given by dKa dA. So that means that the distance between P and Q, so the distance, I should be using blue if I should be consistent here. So the distance between nearby points P and Q that are separated by coordinate differences the Ka, well, that's given by the length of this transition vector from P to Q. I'm going to write that ds squared. So this will be the length of that vector squared, which is just that we insert this vector into the metric. So that would be d Ka dA, and we have to insert it also in the second argument, so d Chi b dB. But now the metric is linear, so we can move these coordinate differences outside, and we are left with g dA dB, d Chi A, d Chi B, and this thing that we have here, that's just the definition of the metric tensor components. So this would be GAB, d Chi A, d Chi B, and this is called the line element. So ds squared. Now note that there's a very strong similarity here to the metric tensor itself, which I write in terms of its components, and then the dual vector basis. So in this expression, of course, these two objects are the coordinate basis for dual vectors, whereas in this it's just the coordinate differences, but it's just to see the similarity here. So the point now is that if I know ds here, if I know how ds is expressed in terms of the coordinate differences, I'm going to be able to extract the components of the metric tensor. We're going to use that later. Any questions? Okay, so then comes the question, I mean, we're talking geometry now. So one thing that we will, and we talked the distance between infinitesimal points. But the point now is that we can use this to express the lengths of curves, for example. So that's a geometrical properties. So the length of curves, which when we get to the physics part in general relativity, that's going to be related to the proper time of the world line of an observer. If you, when you come to that part in special relativity, if you're taking special relativity now, you will see it, but we will also discuss it in detail for the case of general relativity in upcoming lectures. So the length of curves, if I take now a curve, this is a curve inside my manifold, and I can call this curve gamma, and it has some curve parameter, which I'm going to call tau in this case. So I can ask the question, what's the distance along the curve from point A to point B? And just for definiteness, I'm going to put tau equal to 0 at A and tau equal to 1 at B. This is not a requirement, it's just so that I can write the integration boundaries in a simpler way. So in order to answer that question, well, we know what the expression for a small distance is. If we take 2 points here on this curve that are very close together, I know that the distance is ds, and I know how to express ds. So what I can do is that I do this for a long train of small displacements along this curve. And what I end up with is that the length of this curve gamma, that's just summing up all of these small small contributions of ds. So along gamma from A to B, I will integrate this ds. And since I have the this parameterization, I can rewrite this as the integral from 0 to 1 of the metrics. I should have a square root here of chi dot A dA, chi dot B dB, and then I can take the tau squared out of the square root, and I only have d tau. So this would be 0 to 1 and GAB chi dot A chi dot B d tau, and the dot here denotes a differentiation with respect to tau. So any questions so far on that? So one question I can now ask myself is, if I have 2 points, these 2 points A and B, I can ask myself, what is the shortest path between A and B? So for example, it might not be this path, but it might be some other path like that, or even like that, or like that. We just don't know yet. So the way of finding out what the shortest path is to perform variational calculus. So if we take the variation of this curve length and put that variation to 0, this will mean that we'll have an extrema of the curve length. So finding this extrema of the curve length is going to correspond to finding a differential equation for the coordinates in terms of the parameter tau. So what I'm going to do now is that I'm going to call this thing here, I'm going to define it as L. It's a function L, which is a function of the coordinates and of the coordinate derivatives. And to satisfy this requirement, that's equivalent to doing variational calculus and satisfy the Euler-Lagrange equation for this L. Actually, let me do what I did in the lecture notes. So I'm going to actually define this as the square root of L, which is going to make life simpler. So the Euler-Lagrange equations are going to take the following form. So I take the derivative of this integral with respect to the coordinate chi a minus d tau, and the derivative of this square root with respect to the d chi dot a. And in order for the variation to be 0, this needs to be 0. So I can perform these derivatives, and what I will end up with is the following. So 1/2 square root of L dl d chi a minus square root of L d tau, and that acting on 1 square root of L d L d chi dot a. Okay, so that's just performing these derivatives of the square root of L and replacing it by the derivatives of L with respect to the coordinates and the coordinate derivatives respectively. So what I can note here is that I have a square root of L appearing in many places, and I would like to get rid of this. So what I always can do is that if I have a curve like this, any curve, I can reparameterize the curve in such a way that the tangent vector is of unit length. So what I'm going to do is the following, is to reparameterize the curve such that this square root of L is always equal to 1. And if I do that, then of course this is a constant that I can take out of the derivative. It cancels this one, and this is just a constant which I can multiply with, and it doesn't affect anything because it should be equal to 0. So this is equal to 1 over 2 then, and then this thing. So dl d chi a minus d tau dl d chi dot a. And this should be equal to 0 still. And if you look at this, putting this equal to 0, that's exactly the same equations we would get if we were extremizing, instead of extremizing the path length L, we would be extremizing this thing instead. So having L itself rather than the square root of L in the integral. So this is actually a much nicer expression to handle just because it doesn't have the square root. Questions? Okay, so just to continue now, what we obtain from this in the end. So there are some steps to this, but I'm going to skip the actual computation. You can find all of the steps in the lecture notes. So in the end, if we go through the math here, we will arrive finally at an expression that looks as follows. So chi double dot d, so the second derivative of the coordinate d with respect to the curve parameter, plus 1/2 gdA multiplied by 2 dc gab minus dA gbc chi dot b chi dot c equal to 0. And just to mention that one thing we have used in getting this is the following expression. We discussed it a little bit yesterday, but just based on the chain rule, a derivative with respect to tau can also be written as chi dot a dA. In particular, we have used this in this direction when obtaining this second derivative. Okay, so this is called the this is an equation that looks very familiar somehow. So if we remember what we talked about last time, so I'm just going to see if I can find that. Yeah, so I'm going to copy this. I'm going to paste it here. And I'm going to make it red. So if we compare now this equation that we got from searching for the extrema of the curve length to the geodesic equation, which we found by requiring that the tangent vector of the curve should be constant at all times, you see that it has exactly the same structure as we discussed also. This thing is equal to this second derivative just on the merit of this. So these are the same terms, just I exchanged D for B. And all of this second term here, it has the same structure as this, as long as these connection coefficients are given by this prefactor here. So these are the geodesic equations if the connection coefficients, if the connection coefficients, well, actually the connection coefficients multiplied by this, if that's equal to 1/2, and now GBA, let me exchange D and C there. So 2D, let's do C, the D and B, DC GAD minus DA GDC chi dot D, oops, sorry, chi dot C. So if this is true, then we have the geodesic equations. And one thing to notice here is that this may be true for several different connection coefficients. However, it only tells us about the symmetric part of the connection coefficients, because we have here the same thing, chi dot A and chi dot C. So this means that this only tells us about the symmetric component of these connection coefficients. So there may be several metrics that satisfy this, but it does tell us about the symmetric components. So with that said, we're starting now to get a connection between the connection that we discussed last time and the metric. The geodesic equation here, well, it's the same. These connection coefficients relate to the connection, which kind of defines what it means for something to change along a curve, and to the path length here the shortest path essentially between 2 points. So we need some sort of deeper correspondence between the metric itself and the connection. And that is provided by requiring that the metric and the connection are compatible. So metric compatibility. And it's a rather straightforward requirement. So we say that a connection, if we have a metric, a connection nabla is metric compatible if and only if the connection in direction x acting on the metric tensor is equal to 0 for all vectors x. That is to say, the metric is parallel under this connection, or in the sense constant under this connection. So this is what we mean by metric compatibility. And this also has a further interpretation. So this is kind of the basic definition. But if we look at the interpretation here, so let's see what it means for two parallel transported vectors. So let's take a curve. As usual, we take a curve something like that. And we take a vector x here, and we parallel transport it over here. And we take another vector, which we call y, and we parallel transport it to the second point. So we can now ask ourselves, if we have these vectors here and parallel transport them over here, and we have a metric here, then we can compare the inner product at P of x and y. So we evaluate this at P with the inner product of these x and y at the point Q. So essentially, we're going to parallel transport everything here. And what we know is that this inner product here, it's a scalar. It's a scalar field. So we can take its derivative along the curve. So we take the derivative of this scalar field gxy along the curve. But we now know that if we have a metric compatible connection, then, well, we can use the product rule, first of all. So this is going to be the connection acting on G. That's a rank 2 tensor. It acts on x and y, plus G acting on the derivative of x, y, plus G acting on x and the derivative of y. So that's just the product rule. However, we now know that, well, we assumed that x and y were parallel transported along the curve. And that means that their derivative along the curve is 0. So that means that this is 0 and that this is 0. But if the metric now is also, if the connection is metric compatible, that also means that the connection acting on the metric is going to be 0. So this thing is also 0. So everything here is equal to 0, which means that the derivative of this inner product is equal to 0 along the curve. So this means that the inner product between x and y here, which essentially gives the angle and it gives the length of vectors, is going to be the same in P as it is in Q. So if I parallel transport x and y from P to Q, these two are actually going to be equal to each other, assuming that the connection is metric compatible. So if we have a connection that is compatible with the metric, then the parallel transport conserves lengths and angles between vectors. That's worth writing down. If the connection is metric compatible, then parallel transport preserves lengths and angles between parallel transported vectors. Now that can often be used to solve the differential equations for a parallel transport in a simpler way, simply by saying that if I have a vector x here and I want to find the parallel transport of x to this point, and I know that my connection is metric compatible, then I know that I can write down the length of x as a constant of motion, which allows you to get rid of one of the differential equations. Questions on that? Okay, so we have a couple of minutes left, so I want to just briefly discuss the next subject. So that's the so-called Levi-Civita connection. And as I said, Levi-Civita was one person, not several persons. It's just that it's a double surname. So the Levi-Civita connection, so given a manifold with a metric G, if as I have said before, the connection is not unique necessarily. We can have several different connections. Metric compatibility is also something that may occur for several different connections. However, then there is a unique connection, which is both metric compatible so that's just saying that this is true, but also second, it's torsion free. That means that TABC, which was gamma ABC minus gamma CBA, should be equal to 0. If you require both that it's torsion free and that is metric compatible, there is only one single connection that satisfies this, and it's called the Levi-Civita connection. Now we can go back and we can look at this. So we saw, first of all, here, we saw that this requirement of minimizing the or extremizing the curve lengths was very similar to the geodesic equation. And we saw that this actually told us about the symmetric part of the connection coefficients. So we could actually get the symmetric part of the connection coefficients out of this. We can just identify them here with the right-hand side. But now we also have that for the Levi-Civita connection, the anti-symmetric part should be 0. And if I know both the symmetric part and the anti-symmetric part, I know everything about it. So this means that I can get out the connection coefficients of the Levi-Civita connection. So that's going to be GDAP. It's 1/2 GDC DAGCB plus DB GAC minus DC GAB. And this indeed satisfies both this relation and it's torsion free because it is symmetric in A and B. So these are the connection coefficients of the Levi-Civita connection, and if you remember our discussion from Euclidean space, they are actually the Christoffel symbols. So the Levi-Civita connection has the Christoffel symbols as the connection coefficients. And when we are talking about general relativity later on, we are always going to use this Levi-Civita connection. So so far today we discussed the introduction of a metric, and we also discussed how we can find a connection that is compatible with the metric and torsion free, and we arrived at this Levi-Civita connection. Before we move on with discussing the curvature of this metric, I just want to briefly discuss the subject of induced metrics, which some will be very interested in particular since I think it's on the homework problem. So given now that we have discussed metrics and we have discussed maps that take metrics from, or rather take tensors from one manifold to the other, assuming that we have some map between them. Let's discuss now the induced metrics, which is to say that if we have an embedding or immersion, so given an immersion of some manifold M or M1 into a different manifold, M2, so that is that I have my manifold M1 and I map it to a second manifold M2 such that the tangent space mapping between tangent curves between tangent vectors is invertible essentially. So I'm going to call this F. So this immersion F is a mapping from M1 to M2. Now, if I have a metric here that lives over here on M2, then that is going to induce a metric on M1. So if a metric G exists on M2, then this induces a metric which I can call G tilde, and that is given by the pullback of G to M1 by this immersion F. So essentially what I'm saying is that if I take a point here in M1 and I ask myself what's the length of a vector here in M1, well, by definition, or I can take two vectors, G and W, V and W. By definition of G tilde now, so G tilde of V and W, since it is the pullback of the metric G to M1, that's going to be given by the push forward of V and the push forward of W evaluated by the metric that we have in M2. So essentially it means that we are using, if we take curve lengths, for example, if I have a curve here in M1, that corresponds here to a curve in M2. And what I'm using to determine the length of this curve in M1 is just how long the mapped curve to M2 is. So I'm using the metric of M2 to determine the geometrical properties of M1. So we can exemplify that because it's always easier with an example. So we let M1 be the sphere, so the two-dimensional sphere, and we let M2 be three-dimensional Euclidean space. Now on three-dimensional Euclidean space, we have a metric G such that the line element here, ds squared, is just dx squared plus dy squared plus dz squared in Cartesian coordinates. So the question is, what is the induced metric here on the sphere? In order to find that, well, we are embedding the we are embedding the sphere into R3, and we do it the usual way. We let x be, well, let's put the sphere of radius r. So we have sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. This is the standard embedding of a sphere of radius r into R3. So the question is, what is the line element on the sphere that is induced by this? So the easy way of doing this is just to take the same ds. So as I said, we're going to use the length of the induced curve here to express the length on the length of the curve on the sphere. So this is going to be this very same thing, dx squared plus dy squared plus dz squared. But now we know what x, y, and z are in terms of the coordinates on the sphere, which are phi and theta. So what I can do here is that I'm going to take dx, and when I do that, I differentiate this entire object. And what I will find is that if I do that, I get minus cosine theta cosine phi d theta plus, no, plus, right? The plus goes there, sorry. Plus goes there, and the minus goes here. Minus sine theta sine phi d phi. And I do the same thing for the y and the z. And then I insert it into this expression for the line element. And doing the math, what I will end up with is r squared d theta squared plus sine squared theta d phi squared. And this should now be equal to the line element of the induced metric. So this is g tilde theta theta d theta squared plus g tilde theta phi. Well, actually, there's a 2 because it's symmetric. D theta d phi plus g tilde phi phi d phi squared. So what I can do now is that I can just identify the components of the metric tensor here, or the induced metric tensor. So g tilde theta theta, that's going to be whatever coefficient multiplies d theta squared on the left-hand side. So I can identify this with this. Well, actually, with a prefactor of that, which is r squared. So this would mean that g tilde theta theta is equal to r squared. If I do the same thing for the off-diagonal term, g tilde theta phi, which is equal to g tilde phi theta, there is no cross term on the left-hand side, so this must be equal to 0. And finally, g tilde phi phi, that's the prefactor of d phi squared on the left-hand side, so it's r squared times sine squared theta. So this is the easy way of computing the induced metric when you have an embedding of a manifold in, for example, R3. that you just look at the line element and you express the line element in terms of these coordinate differences instead of the coordinate differences in R3. Okay, so that about induced metrics. Let's move on to what we can say about the curvature when we have this antimetric. So the metric is clearly related to the geometry of this manifold. It describes angles. It describes lengths and angles essentially of vectors. And the curvature is also somehow related to the geometry. So the question becomes what we can say about the curvature tensor when we have this Levi-Civita connection, and what kind of statements, what kind of simplifications we can make for the curvature. So when we have a metric, it's going to be rather easier sometimes to work with a different object than the Riemann curvature tensor, which was this 1,3 tensor. We can introduce the 0,4 tensor, which is essentially the following: RABCD. It's a 0,4 tensor, which means that it has 4 covariant indices, and we obtain that tensor just by lowering the upper index of the Riemann curvature tensor. So, I mean, one can consider them in some sense to be in one-to-one correspondence to each other, and sometimes you will just refer to this as the curvature tensor as well, just with all indices down. So, if we do this for the Levi-Civita connection, we can write out the form of this curvature tensor. So it's going to follow here that R, A, B, C, D, and note here that, well, this index is actually the first index. The index that we lowered here is the first index of this expression. So we're going to have an expression now. It is going to turn out to be 1/2, and then it's going to contain a lot of second derivatives of the metric components. So dA, dd, gbc, plus db, dc, gad, minus dA, dc, gbd, minus db, dd, gac. So that's one of the terms, and plus GFH. I know there's a lot of terms here. Gamma BCF, gamma HAD, minus gamma BDF, gamma HAC. So lots of things to take in here. But this is the general expression, and the gammas here are, of course, the Christoffel symbols of the Levi-Civita connection. However, this can be simplified in many cases, and it's particularly useful if you can find a coordinate system where the Christoffel symbols are 0. And when are the Christoffel symbols 0? Well, the Christoffel symbols are 0 in, well, a Christoffel symbol are 0 in one point, let's say. So if in a point P, gamma ABC is equal to 0, so all the Christoffel symbols in that point are 0, then of course this expression is going to go away, and you're going to be left with this curvature tensor being given by the second derivatives of the metric tensor in those coordinates. And this can be very useful sometimes when you need to make actual computations. And let me say that this is given a point P, it's always possible to find such a coordinate system. It's always possible for a single point to find a coordinate system where the Christoffel symbols are 0. And that's in the end going to be equivalent, since the expression for the Christoffel symbols include these first derivatives of the metric tensor, it's going to be equivalent to making sure that all of the first derivatives of the metric tensor are 0. And then this curvature tensor is going to be given by the second derivatives of the metric tensor in those coordinates. Okay, but the point we want to make here is that we're going to be able to look at this expression, and we're going to be able to reduce the number of degrees of freedom that we have in the metric tensor, because in the curvature tensor. Because if you just look at the curvature tensor and you say, oh, this is a rank 4 tensor, you would a priori think that it can have n to the 4th different components, because each of the indices can take on n different values, so the dimension of the manifold, which gives us n to the 4 different components. However, if we look at this and we look at the symmetries of this, well, first of all, we introduced the metric tensor, the curvature tensor, to be anti-symmetric in those two, in C and D here. So we already know that R, A, B, C, D should be equal to minus R, A, B, D, C. So that's exchanging those two indices. So that removes a lot of the degrees of freedom from this tensor. However, if you look at this expression and you change the roles of A and B, so A and B here change, which means, let's see, not that one, but that one. If you compare those two terms, they are the same terms if you change A and B, just with a different sign. And the same goes for these two terms. It's the same if you change A and B, just different signs. It's also true for this one. So this means that if you change the position of A and B, you also get the minus sign, which is another symmetry then, or rather anti-symmetry of the curvature tensor. And finally, if you exchange the set AB with the set CD, you will see that this expression again is the same, which means that this is also equal to R, CD, AB. So in this case, we had the first two indices changing, and in this case, we actually have groups of indices changing. So these are symmetries of the curvature that we can use. So let's say that we, for some case, we have R1, 2, 1, 2. If we have that component, we can immediately express R2, 1, 2, 1 to be equal to that. So we're decreasing the number of degrees of freedom that we have in this curvature tensor. And there is also an additional relation that is true for the curvature tensor, and it's the so-called Bianchi identity, which I'm not going to derive. I'm just going to state it, and it is that Rx, Y, Z, if we make a cyclic permutation here and add them all together, Ry Z X plus R Z X Y, this is equal to 0, and it also gives a relation in terms of the components. So this is essentially going to tell us that R, A, B, C, D, and then the cyclic permutations of the three later indices, R, C, D, B, plus R A D B C equal to 0. So this again gives us some relations among the components of the curvature tensor. All in all, we are going to be left with in general n squared times n squared minus 1 divided by 12 independent components. Of the curvature. So in essence, we only need to compute this number of curvature components. And then we will be able to express all other curvature components in terms of those. So for example, if I take here n equals to 2, so if I have a two-dimensional manifold, then I have 2 squared times 2 squared minus 1 divided by 12, which is 4 times 3 divided by 12, which is just 1. So if you have a two-dimensional manifold, it's going to be sufficient to compute a single curvature component, and that is then going to tell you about all other curvature components as well. Any questions? So there is an example. I don't think I have time to go through the example, but on page 26 of the lecture notes, there is an example of computing the curvature components of the sphere. And I said I would suggest that you look at that, because it's a nice example, and it also shows you how to a good way to compute the components of the curvature tensor. So just a few definitions is the following: the Ricci tensor, and these are definitions that are going to become important when we look at general relativity, because they are going to appear. So the Ricci tensor, it's a 0-2 tensor, and it's defined by, so I'm going to write it RAB. It's defined by contracting here two of the indices of the curvature tensor. So the upper index with the middle index of the curvature tensor. If you contract those indices, you get what is called the Ricci tensor. We also have the Ricci scalar, which, as the name suggests, is a scalar, and that is, if we have a metric, it's going to be the trace of the Ricci tensor. So I'm going to write it R, and it's GAB, RAB. Or if you want to express it directly in terms of the curvature tensor, GAB, RC, ACB. And finally, what is called the Einstein tensor. It's a combination of the Ricci tensor and the Ricci scalar. So GAB, it's the Ricci scalar itself. RAB minus 1/2 GAB times the Ricci scalar. But for now, those are just definitions. Because I want to have 15 minutes left to talk about the last thing that we will talk about in this mathematical prelude. And then next time we're going to be able to start looking at the physics of general relativity. So the last mathematical concept that we're going to discuss is so-called killing fields. Now, these are not fields that go around murdering people. It's named after a Norwegian mathematician whose last name was Killing. So the question is, what are they? So the short and kind of boring definition is that a vector field K is a killing field if its lead derivative, or sorry, if the lead derivative of the metric in the direction of the killing field is equal to 0. Now, what does this mean? Well, it means that we have some sort of symmetry of our manifold. So just to take an example of this, I'm going to look at the sphere again, because we love looking at the sphere. No, not an ellipsoid, a sphere. So if we look at the sphere and we look at the embedding of the sphere into Euclidean space, as we did, you know that it has some symmetries. You can rotate the sphere, for example, and that would be a symmetry. It would induce exactly the same metric on the sphere if you make this rotation. So a rotation of the sphere, so I'm rotating these points like this. If I make this rotation, I don't change the metric that I induced on this sphere. And this metric and this rotation is a continuous rotation. And since it is a continuous rotation, well, you have a family of curves here, which are these circles. And since we have these circles, this family of curves, it corresponds to a flow of some vector field. And that vector field is exactly this vector field K that we're going to be talking about. So it's a symmetry of the sphere, and we can argue, I don't have time to make a longer argument about it, but if you do this, if you compute the lead derivative of the metric for this killing field that generated this symmetry, this rotation of the sphere, you're going to get 0 for this derivative, for this lead derivative of the metric. So in essence, what we're saying here is that if you have a field whose flow lines generate this symmetry, then the lead derivative of the metric is going to be 0. So these killing fields, and in particular then their flow, the flow of those of a killing field represents some sort of symmetry of, in this case, the sphere, but in general of a more of a general manifold. So let's just take this example here. If I look at this example, and if I look at the field that would generate this rotation, it would just be that K would be equal to d phi. That's just a rotation around the z-axis, in essence. And we can verify then that this is a killing field by computing this lead derivative. So let's look at LK acting on G, and let's look at the AB components. So we know what the metric components are. If we take a unisphere, so I take away the r squared, g theta theta is 1, g phi phi is sine squared theta, and g theta phi is equal to g phi theta, and both equal to 0. So I can compute this lead derivative. In general, it's going to be given by d phi acting on GAB. So that's the derivative of the metric. And since I have a second order tensor, if I take the lead derivative of a 0 to tensor, I'm going to have two terms with a plus sign. And this is going to be GA phi dB, and then acting on the phi component of K, and the phi component of K is 1, plus G phi B, and then the A acting on the phi component of K again. So 1. Now, both of those derivatives are 0 because 1 is a constant. And if we look at the metric components here, GAB, well, none of these components depend on phi. So all of these derivatives are also 0, which means that regardless of what I put A and B to, this is going to be 0. And I obtain that this vector field K is indeed a Killing field. And of course, the corresponding flow lines are that theta goes to theta and that phi goes to phi plus the curve parameter. This is a rotation around the z-axis. So with that said, the last thing I want to say regarding just mathematics, essentially, is the following. So just to make a slight change from this, because it can be quite not completely clear what this implies for the field K, or what kind of restrictions it puts on the field K. But for a metric compatible connection, we're going to be able to rewrite things here. So we can start from this, and the full computation is again in the lecture notes. We're going to start from 0 equal to LK GAB. And we're going to express this. Well, actually, we have 5 minutes, so maybe we can do the actual computation. The general expression here is that this is KC DC GAB plus GAC DB KC plus GCB DA KC. So essentially, this is the reason why I had this expression here. It was just performing the first term here is this term, and this term is that term, and this term is that term. So what I can do now, assuming now that I have a metric compatible connection, I'm going to be able to express this derivative of the metric tensor in terms of the Christoffel symbols. So what I end up with is something as follows. So I'm going to write first the two other terms, dB kc plus gcb dA kc, and then using the metric compatibility, I get kd gamma cdA gcb plus gamma cdB GAC. So the only thing I have done now is to use the metric compatibility to rewrite this derivative in terms of the Christoffel symbols. But now I can collect here. I can collect from this term. I have a GAC, and I have a GAC there as well. So I can collect that term. And then I have dB KC plus gamma dB C KD, and plus the corresponding term then for the other one. And what we note here is that this expression, that's nothing else than the covariant derivative of Kc. So what I end up with is GAC nabla B Kc plus the similar thing for GCB, nabla A, KC. But since we had a metric compatible connection, this metric can be moved inside the derivative here in order to lower the C index, and the same thing here. So what we end up with is nabla B KA plus nabla A KB, where KB is GBC KC. So all of this boils down to that this, and you will see this pretty often as the condition for a field to be a killing field, that it's this symmetrized derivative of the covariant components of K should be equal to 0. And if that is true, then you have found a killing field. If this is solvable, of course, there is no guarantee that you can find killing fields. If the space you're looking at has no symmetries, you will not be able to find a killing field. But if this is solvable, then yes, then you have found yourself a killing field and the symmetry of the manifold.